Hello everyone, and welcome back to another Geostats lecture video. And in this lecture video, we're going to talk about how to calculate Morans I using R. So it's actually a really simple one-line function call to generate Morans I, and it's again going to be coming from the spdep package. So the actual function call is going to be moran.test. So you'll see we have the Morans I test for spatial autocorrelation. And you'll see here the three parameters that we really need to worry about are the x, the list w, and then this randomization equals true. And this randomization equals true is important because this controls which one of the p-values we're going to calculate, whether we're testing it against randomization or we're testing it against normality. So let's look at the other two. The first parameter is this x parameter, right? The numeric vector. So this is the variable of interest. So in our example case, we're going to continue on talking about that Georgia data set and the percent rural variable that we've been talking about up to this point. And then the list W here, this is that spatial weights matrix that we've went through in the previous videos and set up. So what I've already done, and if you don't already have these 4 lines of code, I would encourage you to go back and grab them or just pause the video right now and catch up. All I've done is I've taken the first function here, this poly to NB, which again converts polygons to a neighborhood connectivity matrix. And then we have this NB to list W function, which again converts from the neighborhood connectivity to the spatial weights. And again, we have both the rook and the queen case. So these 4 lines of code we've already talked about in detail. If you don't understand them, I would encourage you to go back and watch those videos and just make sure that you have them if you're following along. So what we're going to do to run the Morans I test is we're going to call again, we're going to do the rook case first. We're going to do rook underscore Moran. And I'm going to put random because we're doing the randomization assumption first. And again, we're going to call the spdep package, and we're going to call moran.test. Okay. And so the contextual menu says we need the x, we need the list w, and we need the, again, you don't necessarily have to call randomization equals true, but I always find it's extremely useful because it, again, if somebody's reading through this code or if you're reading through this code later, you don't have to remember what the default setting was. And this again just says that we're testing the randomization. So just to review what that means, we're testing the assumption that the variable of interest is random, which means that any value is equally likely. So if the null hypothesis in this case is that any value is equally likely, which means if this is false, that every value is not equally likely, which is, again, we could reject the null hypothesis, and we would be able to say with some level of certainty that the data is biased in some way. Typically, this is an indication of autocorrelation. All right, so what is this x parameter? Again, the x parameter, this is our data of interest, so we're going to call GEORGIA for the Georgia data set. Oh, we actually have to load all this. Let's go ahead and call our data equals data equals Georgia from GIS tools. I'm going to run these 4 lines of code really quick so that it knows what we're talking about. Okay, so now we can get back here. So Georgia at data $, and then we want percent rural. Oops, percent rural. Okay, so this is our variable of interest. Our list W, this is our spatial weight. So this is going to be the rook underscore SWM for the rook's case spatial weights matrix. And if we run this, we don't get any errors. If we go here and we type in rook underscore Moran underscore random and we run that, you'll see here this is what we get back from the sort of printout. And what we get is the top saying we've run the Morans I test. It's telling us a reminder that we're using randomization. It's repeating that we have data in a weights matrix. These should hopefully match up with your inputs. And then down here we get the p-value and the Morans I statistic. So as we've mentioned in the conceptual videos, again, right, the statistic, you kind of need a little bit more information to be able to really interpret it on an absolute scale. But what we can certainly do is we can certainly look at this p-value. And this p-value here is less than 0.05, although it's not insanely low. But it is an indication that we might consider rejecting the null hypothesis, which again tells us that we have an indication that the data is not random, which is an indication of some sort of correlation, and we're assuming here that that is spatial autocorrelation. So we can do the same thing for normality. I'm just going to copy this rather than retyping everything. I'm just going to copy this. I'm going to change this from random to normal. And I'm going to change randomization here to false. So by changing randomization to false, I have now told R to test for normality rather than randomization. So if I run this, we still don't get any errors, which is always a good sign. And if we call rook underscore Moran underscore normal, we run that, right? You'll see here that up here this has changed. We are now testing for normality. You'll notice that our Moran test statistic doesn't change. We haven't changed Moran's I. We've just changed what our p-value is testing against. So in this case, our p-value is testing against normality, with the null hypothesis that all of our variable values are coming from the same normally distributed population. So in this case, we are rejecting that null hypothesis. Again, we're rejecting the fact that they all come from the same normally distributed population. So this would again be an indication that our data set has some sort of structure to it, and we are assuming that that structure is coming from spatial autocorrelation. Hopefully that makes sense. Let's do one more, and this time I'm going to type it out again just so you can see it typed out one last time. So let's do the Queen's test for spatial autocorrelation under randomization. So we're going to do Queen Moran, and then we're going to, Moran, and we're going to test for randomization. Okay, so again, the sp package, moran.test. We need an X. We need a list W for the spatial weights matrix. And then again, just to be completely clear to anybody who reads our code, including ourselves in the future, we're going to call randomization equals true. Not true zero, not true dot, true. There we go. So our X is going to be the same thing again, because we're always going to be using the Georgia at data $ spatial weights, or not spatial weights, % rural. And then in this case, our spatial weights matrix is not going to be rook, it's going to be queen underscore SWM for spatial weights matrix. If we run this, no errors, always a good sign. And then if we go down here to queen underscore Moran underscore random, and if we run that, you'll see here, if we compare that, let me slide this up just a touch. So this is the rook's case test under randomization, and this is the queen's case test under randomization. So given this particular data set, you'll see that there isn't too much of a difference. Our Moran's I's are still pretty close together, right? They haven't changed that much. That's a function of the fact that this data set, if you remember back to when we graphed out the neighborhood connectivity, there weren't too many differences in terms of the connectivity, so it would make sense that these are going to be pretty close. But you can see here that we did change the Moran's I statistic slightly, and you'll see here that the p-value did also change slightly, but it's still statistically significant. We can reject the null hypothesis, saying that the data is random, so we would say with some level of confidence that the data is not random, which again is an indication that we have some structure and that we're pointing to that as autocorrelation. So hopefully all of this made sense. And as always, please reach out. Thank you.